Okay, let's go ahead and get started. I am excited about today's lecture.
Yes.
I've been waiting to give this one. This is the most important lecture of the semester. It's a good thing you're not missing this one. This is critical, and the one on Thursday is also critical. What we're going to do is build a gut level model for electric current in circuits, and it's going to require that we keep focused, that we keep kind of working our brain as we go through this. That we and sometimes there's a temptation to just say, you know, I'm going to figure this out before the next exam. No, figure it out right now. You know, right this next hour and 15 minutes, and then everything's going to be really, really easy. When you get to that next exam, if you have a model, actually two models, one for current, one for voltage, if you have those models going into that exam, it's going to be trivial. You're going to be giggling all the way through the exam. If you don't have those models, it's going to be one of the worst experiences of your life. So we want to give you that model, and I really want us to be mentally awake. So is someone willing to pray for us to be mentally awake? Someone that's not a good awake prayer?
I'll say it for you.
You're awake.
As awake as I can be, right? All right, Heavenly Father, we're grateful for this day. We are very grateful for Professor Francis and for the opportunity to be here before you. Father, like Professor Francis said, we pray that we are awake and attentive today, not only in this class, but throughout the whole day, so that we can learn and augment our knowledge. Father, we love you very much, and we pray for Professor Francis and his family, and also us as we're in this midterm season. We pray for an added measure of the Holy Ghost and the Spirit to be with us, so that we can recall what we've learned and do our best. We love and thank thee. In the name of thy Son, Jesus Christ, amen.
Thank you. Okay. As I mentioned, today we're going to build this model for electric current, the flow of charge through the wires, through the bulbs, through the battery. And then on Thursday, we're going to build a separate model for electric voltage. And it turns out that when students are learning about circuits, that's one of the most common confusions. The mistakes that are made are often because we confuse these two ideas. And it shouldn't surprise us that happens, because even the greatest minds make this mistake. This is a quote from David Letterman. He was a late night talk show host when I was alive. And I stayed up late one night because he was going to blow up a 500-pound pumpkin. And I was excited. And I watched, and he didn't do it. He said he'd do it tomorrow. So I watched the next night. And this is a quote. He says, "We're going to try again tonight to explode a half-ton pumpkin. We wanted to do it last night, but the heavy rains put the kibosh to it. It seems the pumpkin had electricity running through it. Here's how. Along the sidewalks of New York City is a metal edge. For some reason, 5 volts of current runs through the metal edge on the sidewalk of 53rd Street. Wrong or sick and wrong? Sick and wrong, sick and wrong. And I was so upset. I was so upset that I contacted the station, and they told me to calm down. And then I was so upset that I actually paid money to buy a transcript of that particular program. So anyway, we're going to do better than David. And we're going to start with 3 quick experiments. And the first experiment is this one right here. What I have is a battery, 12-volt battery, a bulb, and an ammeter. measures current, and you've seen those before. This might be a little bit new for you. This is we call it a rheostat, but it's just a dimmer switch like you'd have in your dining room. Essentially, it's a variable resistor is what it is. And what we see is that as I change the resistance, right now I've got a lot of resistance in the circuit, and so there's not much current. And I'm going to reduce the resistance in that circuit, and you should see two things happen. The current in the circuit goes up according to the ammeter, and the brightness of the bulb, it becomes brighter. Okay, and if I increase the resistance, the current in the circuit goes down and the bulb gets dimmer. Now, the way we say this, the way I like to say it, is more flow, more glow. More flow, more glow. And you see that when I disconnect the battery, I have this ammeter is not quite right, but it should read 0 right now. And when I connect it there, even with a lot of resistance, it went up, suggesting there's current going through there, but I can't see that bulb light. Okay, can you see that bulb light? Okay, so and it may not be lit at all. What the bulb's doing when it lights is the filament is getting hot. This is a Montana example, but if you're working on a horseshoe, you put it in the flames, you heat it up, and eventually it gets to where it's glowing red. And then if you heat it up more and more, it eventually glows white. And that's what you want to do to the filament of that bulb to make it glow. We've got current going through there, not quite enough to make it glow yet. It's not quite hot enough to glow. But we're going to build our model on this principle of more glow, more flow, more glow. And that's how we'll tell where I've got more flow. Okay, the second experiment, I'm going to have to rearrange the room here. Sorry for that. I got to tell you, I looked all over campus to get this whiteboard. Finally, the moving department off campus had one. And so I'm going to take this battery and I'm going to hook it up to a single bulb. Oh, man. So they made this so that I can't hurt myself, so that it's covered, and sometimes it just pops right out, protecting me. Okay, that's not gonna work. I got lots of them. Let's try this one. That one works. Okay. So that bulb is bright. And I represent that with these golden rays coming out. And try to memorize that brightness right there. Because now what I'm going to do is I'm going to put a second bulb. We call this in series. Okay, so I would break that and connect these. And we did this in the tutorial. This is a review. Okay. Now, what we see now is they're dim. And I make that apparent with this lighter shade of gold here. But what we notice is that they're the same dim. They're exactly the same dim if these were identical bulbs made at the same factory by the same worker on the same day. Now, I know that more flow means more glow, so I must have a lot of flow in the single bulb. Let's call that 5. Whether you want to call that 5 amps or I call it 5 quarts of blueberry juice per second, doesn't matter. The flow's 5. And these guys are dim, so they must have less than 5. And because they're the same dim, it's going to be the same size. Now, what we care about and what we're always going to go back to is what's flowing through the battery. That's going to be critical in understanding these circuits. In a simple circuit like this, we know what goes around comes around. And so if that's 5, that's 5. Now, my question over here is, what's flowing through that battery? And these are your choices. Is it that, or is it that plus that? Talk to your neighbor. You're going to vote in just a second.
I can't tell you why. Oh. What? It's not gonna be.
Okay, let's vote. We're going to vote with our hand. Remember, what we're voting on is what's flowing through the battery. Is it this or this plus that? How many say it's this? Raise your hand. How many say it's this plus this? Okay, we divided the class into 2 equal parts. Equal parts. We don't agree on what's flowing through that battery. But I think we do agree, I think we can all agree that those 2 bulbs are sharing the current through the battery. Do we agree on that? Nod. Everyone nod. Yes. Unfortunately, the word share has 2 different meanings. We can share like we share a book. I read the book, I liked it, I give it to you, you read the book, goes back to the library, the book doesn't get used up. Okay? We can also share like we share a pie. I eat half the pie, you eat half the pie is gone. So in this case, those 2 bulbs are sharing the current through the battery like a book or like a pie. Shout it out. Did we say pie? Are you just hungry? What? No. It shares the current like a book. Okay, like a book. Now, remember, something's flowing. We know it's electrons. It might be blueberries, okay? And we take one of those blueberries and we paint him green and we call him Fred. And Fred goes around we always go from the positive terminal around to the negative terminal, okay? Conventional current. And Fred has to go through this bulb. And all of his friends with him. And then he has to go through this bulb. And all of his friends with him to get back to the battery. So it's not that this is the same size as that. It's the same current. It's Fred and his friends there, and then Fred and his friends there. Okay? They just passing through Dodge. Okay, so this is going to have the same current through the battery as through each of these bulbs. See if your neighbor's okay with that. See if they voted wrong.
Sure, it's like
What's that? Oh, because that's less than 5. More flow, more glow. Yeah, they're sharing this book. And it's smaller than
that.
the battery's giving less current. Yeah. Okay. Now, you remember the F net equals MA of this part of the course is V equals IR, V equals IR. And if we use V equals IR, we have to realize that if this has a certain resistance that I just gave a arbitrary value to, this must have more resistance. Two bulbs in series must have more resistance than a single bulb. And because of that increase in resistance and the fact that the voltage of the battery stays 12 volts, it says right here, it's 12-volt battery, okay? If I have a little resistance, I get a big current. That's my 5. If I have a big resistance, I get a smaller current. That's the smaller current, and that's why these bulbs are dimmer. Does that make sense? Okay. Now, we're going to play a game over and over again today. I call it the black box game, and this is the way it's played. I've got 2 identical batteries connected to 2 identical bulbs, and they're also connected in series with these boxes that we cannot see inside of, okay? We cannot see inside of. But we know that when we hook this up, that these indicator bulbs are going to show us what's going on in the battery. I can't see the current flow in the battery, but I can see the glow of that indicator bulb. And that tells me how much current is going on in the battery. So what if I tell you that this indicator bulb is dim and this one is bright? What does that tell you about the resistance of box A versus the resistance of box B? Which one has more resistance? Shout it out. A, yeah, of course, A. So this is how we play the game. I'm going to give you 2 different boxes, and I'm not telling you which is box A and which is box B. That's what you're going to have to figure out. And we're going to get our clicker out, and I'm going to ask you to use your clicker to tell me which box has this left one here is in which box, A or B. So let me get this started. Okay, now you can click. This is an easy one. You can do this in your sleep. Indeed, some of you are.
Right?
Is that everyone?
Yeah? Please.
I'm gonna say I'll answer. So
Okay,
not just
last call. Get your vote in. Last call.
Box A.
Excellent, excellent. Okay, it's B.
I don't know.
Now, this is the way you did it. You said, well, I know that box A has more resistance. And I know that 2 bulbs in series have more resistance than a single bulb. So that means that A must be on the right and B must be on the left. Okay, good job. Now you're tempted, I think, to take away from that the bigger the R, the smaller the current. And if that's your guiding light, if that's what you take away from this lecture, I guarantee you are going to fail the next midterm. Okay? Do I have your attention? Yeah. You have to finish your sentence. The bigger the R, finish your sentence, of the circuit as a whole. Remember, we can take a complicated thing like a stereo and replace it with one single resistor. We call it the equivalent resistance of the stereo. And that's all the battery cares about. Okay? And so the bigger the equivalent resistance of the whole circuit, the smaller the current, finish your sentence, through the battery, Now, we're going to get to some pretty complicated circuits with lots of different paths, different branches. And the current here is going to be different than the current there. Everywhere it's going to be different. But all of that current has to go back through the battery. So that's what we compare is, what we relate is the resistance of the whole circuit to the current through the battery. Let me get that out of the way. Okay. Now, experiment 3, I start back again with that single bulb. Okay, let's do this. Okay, I'm constantly, let's see, that just pops right out. I should have checked this before. I apologize. Ah, that one sticks. We got a sticker. There we go. Okay. So that's my single bulb again. And this time, and you see that it's bright, and we called that 5 amps, quarts of blueberry juice. So this time, what I'm going to do, instead of putting it in series, I'm going to take that second bulb and add it in parallel. And I'm going to do that by just connecting them on this side and connecting them on this side. That one's bright. And it's the same brightness as the one that we started with. And the other thing we notice is that if I turn this one off, it doesn't change the brightness of the original bulb. Okay. And that's what you want in your house. When you turn off the light in the kitchen, you don't want the light in the front room to be affected. So let's talk about what's going through the battery. If these are equally bright and more flow equals more glow, then if that's 5 quarts of blueberry juice per second, that's 5 quarts, and that's 5 quarts of blueberry juice per second. Okay. That makes sense? More flow, more glow. So the question is, what's going through the battery? Well, in the simple circuit, we know what goes around comes around. So that has to be 5 quarts of blueberry juice. But if I'm going to deliver 5 quarts here and 5 quarts there every second, how much do I have to bring into that junction? Count it out. 10. Yeah, this has to be 10. Because if I look right there at that junction, I'm sending 5 this way and 5 that way. I got to bring in 10. Now, what just happened to the current through the battery? It doubled from 5 to 10. And are we sharing like a book, or are we sharing like a pie now? Like a pie. Now we get to talk about pie. Now we get to talk about pie. Okay. Now, if we go back to V equals IR, what that means is that this has some arbitrary resistance that we labeled last time. This must have half the resistance. Okay. I know it's half the resistance because the current is twice as much. Now, if I use V equals IR, again, what I get here is because this is a smaller resistance, I get a bigger current. And because this resistance is half as big as that, my current will be double. Now, double. Now, a word of caution. I've been working with people on the tutorial homework, and what I see over and over again is people come in and say, well, the way I figured this out is I assumed that every bulb in the problem had a resistance of 10 ohm. And then I used the formulas that you taught us last time to figure out which circuit had more resistance. Well, it turns out that doesn't work. And that's because a bright bulb has a different resistance than a dim bulb. Now, wait a minute, Greg. You said these bulbs were identical. If they're identical, they should have the same resistance. No. I said they're identical in that they were made at the same factory by the same worker on the same day. His name is Sven. those bulbs act exactly the same as each other. But in both cases, both bulbs, when they're really, really bright and really, really hot, they have more resistance than when they're cool and not so bright. They're non-ohmic. And that's a feature, not a bug. That's why I like working with bulbs, is because you can't plug into formulas. You've got to have a model. You've got to understand what's going on in the circuit. You can't just plug and chug into equations. Because when you're plugging and chugging, you're not really thinking, you're computing. Okay? Now, in this case, this is an exception. Because all of these bulbs are exactly the same brightness, I know that they're all the same resistance. And I know that two paths are twice as easy as one path if we're talking the same resistance on each path. And so that's how I know that the resistance here is half as much as the resistance there. But in the previous experiment, we had a bright bulb and two dim bulbs. And we can't say that the two dim bulbs had twice the resistance as the bright bulb. They got more resistance because we got less flow through the battery, but it's not twice as much. Okay, so you have to be careful with what you're claiming. Okay, let's play the black box game again. This box on the left, is it box A or box B with your clicker? They're going to get harder, trust me. And keep your clicker out. We're going to do lots of clicker questions today. Last call, get your vote in. Okay, the answer is A. Good. Okay. Now, in summary, when we add something in series, whether it's a single bulb or a network of bulbs or a bloody fish, it doesn't matter. Whatever we add in series is going to affect the current through the battery by making that current go down. And the reasoning is 3 steps. We're clogging up an existing path. And by doing that, by forcing Fred to go through something he didn't have to go through before, we are increasing the resistance of the circuit. And what we find is that whenever we increase the resistance of the circuit, we decrease the current through the battery. Okay, and so the current through the battery goes down. Now, what's important to note, again, is that it doesn't matter what we add, but how we add it. It can be anything. But if we add it in series, we lower the current through the battery. Now, how do I know if I add something in series? Well, if I'm drawing something on a whiteboard, and I want to add something in series, I have to pick up my eraser. And I have to break an existing line and make the bulbs go out. And then I have to add something in that space, okay? And before I added the red part, Fred just had to go through this bulb and that bulb. And now he has to go through this bulb and that bulb, but also something new. This might be really easy to get through, but it's something else. It's something extra, okay? Now, in real life, you have to break the circuit by disconnecting a wire or using scissors. You don't have your eraser, okay? On the other hand, when we add things in parallel, regardless of what we add, we cause the current through the battery to go up. And again, the reasoning is threefold. we are adding a new path, a new opportunity for flow. And in our last lecture, we found that that always increases the flow through the battery. Okay, no matter how hard that extra path is. Now, if that decreases the resistance of the circuit, it's going to increase the current through the battery. And again, it does not matter what you add. It just matters how you add it, okay? How it's added. Now, when I'm adding something in series, in parallel, if I go back to my original circuit here, I can add something in parallel without breaking the line, without picking up my eraser. I just click it on, I clip it on there with alligator clips. And I clip it on there with alligator clips. Okay, and it doesn't matter, there could be 27 bulbs there. It's a new path. It's like the trap door in the ceiling open up and the rope coming down. That is a new opportunity to get out of this room if we're all rushing for the doors. Okay, any new path lowers the resistance, and we can, if we don't have to break the circuit, if we can just clip on the new stuff, we've added it in parallel. Yes.
Even though you added a whole bunch of things in series in that added parallel, it still will decrease the resistance?
Yes, there can be 1,000 bulbs in series, and if I add them in parallel, that's a new path. Yes, it is. And that simplifies things, okay? I don't have to count and say, is this too many bulbs? It looks like a lot. We don't have to care, okay? Yes.
So if we were comparing two circuits, and we had 1,000 bulbs added in parallel, and then we had 2 bulbs, is the difference there? Would they have the same current or different current? I'm thinking they would have different current.
Different current, yes. And we're going to get there. Patience, young Jedi. Okay? What we're going to find is that there are 4 ways to change a circuit. 50 ways to lose a lover, 4 ways to change a circuit. Okay? Now, the first way is we add a new path. And I hope everyone can see what that new path is. To get from here to here, we added that extra bulb right there. Okay? Now, in every case, that's going to reduce the resistance of the circuit. That's going to increase the current through the battery. Now, if adding a path lowers the resistance, removing a path, going backward in time here, is going to increase the resistance and decrease the current through the battery. Okay, so that's 2 of the ways. We can also change a circuit by cluttering a path, an existing path. Okay, and so here I took that path right there and added an extra something right there. And by cluttering that path, I've increased the resistance of the circuit. I decreased the current through the battery. Again, I can run time backwards and declutter the path by taking that bulb out and reconnecting the wire. I am decluttering a path, and that's going to lower the resistance of the circuit and increase the current through the battery. Check that your neighbor understands these 4 ways to change a circuit.
Yeah.
Hey, can't help it laugh.
Just like.
So. Current. How much help that?
Okay, the question is,
Or a book, it's like, if you have 3 things.
when I'm adding these bulbs, I'm increasing resistance. Well, what about your example over here, Greg? Well, the example over here, I started with just this
Oh, yeah.
and added this path. Well, here, that path was already there, and I just cluttered it up. Okay, if I was starting with this and I added that, I would be lowering resistance because that's a new path. But I'm cluttering up an existing path by putting this bulb right there. In order to put this bulb right there, I've got to pick up my eraser and break that line and shove it in. You see the difference? No? Okay, if I go. Okay. If I go from here to here, that lowers resistance. But if I go from here if I started from that, and now I pick up my eraser and I break this line, adding something else that has to go through that didn't exist before, that increases resistance. If I added this bulb, that's going to increase resistance. But if this was a new line that didn't exist before, that lowers resistance. But this was an existing line and I cluttered it up. Okay. Okay. Did you have a question as well? Okay. Let's move on and practice here. We're going to use our clicker here, and I want you to tell me which of those networks has more. Oh, don't. I'm not starting yet. Wait, there's more. There's more. Okay. Now the question is, which has more resistance, A or B? Now you can click.
Yeah.
The tip, right?
Adding something in. Can you imagine?
Oh, well, we're going to talk about that. Sorted out. That's you didn't change the circuit at all. Now. Okay. Last call. Get your vote in. Okay, the answer is A. Now, notice not all of us chose A, okay? And the people that didn't choose A are the ones that took their shoes off. Now, you didn't smell their feet, but I did, okay? I smelled their feet, their stinky feet. And this is why they took their shoes off. They've got some complicated method going on in their head where they say, oh, bulbs are bad. And so on their fingers, they count the bulbs on B and the bulbs on A, and they, oh, lots of bulbs on B. And then they remember, oh, paths are good. But they've already used their fingers, so they take off their shoes and they count the paths on their toes. Okay? If you take off your shoes during the exam, bazinga, you're mine. I will crush you. It is so much easier than that. It is so much easier than that. What you do is you take out a red pen and you circle the new stuff. What did I have to add to this to turn it into that? And here's the key. You don't care what's in the circle. It can be a huge network. It can be a bloody fish. You don't care. All you care about is how was it added? Did you cram it into an existing line, or did you clip it on with alligator clips as a new opportunity for flow? In this case, we clipped it on right there, and we clipped it on right there as a new path that didn't exist before. And so that means the resistance of this is going to be less than the resistance of that. Yes.
So we added something in parallel here, but what would happen if we also added something in series?
At the same time? I'll get to that. Hold on, young Jedi. Okay, now. You remember that in Physics 105, the most important tool you had in your toolbox when we were doing dynamics problems was the ability to draw a free body diagram. If you could draw that correct free body diagram, you were golden. But if you couldn't draw the correct free body diagram, you had no chance, absolutely no chance of getting the problem right. Now, in these circuit problems, the most important tool you will have in your toolbox will be looking at two separate branches, two different paths, and saying, that one has more resistance than this one. And if you get that wrong, you're just wasting your time on the rest of the page on that exam, okay? So that's something that you have to always get right. You have to be able to always make that determination. So let's play our black box game. This time we'll just shout out the answer. We're not going to use our clicker on this one. Is the box on the left box A or box B? Shout it out. A. Yep, I circled the new stuff. That's on an extra path that didn't exist before, so that lowers the resistance. And so that's box B on the right and A on the left. Okay, one more. Box on the left, A or B? Shout it out. An almighty shout went up in the land. Is that A or B, people?
Let's be. I don't know.
Circle the new stuff. Well, that new stuff is a parallel network, Greg, and I don't care. I don't care what it is. I ask myself, how was it added? And if I started with a single bulb, and I wanted to add that network, I'm going to have to break the line and I'm going to have to add that in. Now, two bulbs in parallel, it's easy to get through, but it's something extra that didn't exist before in that line. Fred used to only have to go through this one bulb, and now he's got to go through that bulb and this network. And this network could have lots of paths. It could have 27 paths, okay? It's still something extra. And so that means that we have increased the resistance by putting in that network. So the one on the right is A and the one on the left is B. Questions on that? Okay, one more. The box on the left, is it A or B? Shout it out. We're not really good at this game.
Yeah, it's B. Left is B. Why is it? Hey, I don't understand why they're doing.
Okay, there's the extra. When I put that in, did I need to pick up my eraser? Yes or no? Yes. And so that means it's added in series. So it is going to be increasing the resistance. So the box on the right is A and the box on the left is B. See if your neighbor is comfortable. Otherwise, we're going to have to slap them.
The bond.
Yeah.
You about to get slapped? Yes. I'm glad you're.
Okay.
I can't.
Now, with your clicker, which circuit has more resistance, A or B? We're just going to keep on practice.
Yeah.
Yes, true.
Yeah.
Straight, left or right?
Stuff is so funny now. It's a new prom. We don't care what the new stuff is. Oh, yeah. B has more.
There it is.
Okay. Last call. Good enough.
Look at my hand out like.
Oh, okay. So most of us got that right, but not all of us, not all of us. So, and some of us voted E. Okay. What I do, I jumped ahead here. I circle the new stuff and then I ask myself, did I add that in series or did I add that in parallel? And I added it in parallel. But some of you are saying, well, look, Greg, it's in a straight line. That's not what series means. Okay. That's not what series means. Did I need my eraser to add that? Okay. This is the way you compare the resistance of two circuits. This will always work. Okay. This is the way you want to do it. You draw the two exactly the same. And I start with the simplest one. Okay, and if I draw that upside down, that's not going to change anything. If those were my two circuits, they would have exactly the same resistance. And then I ask myself, what's missing? And what's missing is those two bulbs in the middle. Did I at any time pick up my eraser? I did not, okay? Now let me do that over again. If I do that like that, is that the same circuit as A? Yes. Yes, it is. And so I added that as a new path that didn't exist before. And so that means the resistance of this on the left is less than the one on the right. Okay? How we doing? Check on your neighbor. Buddy check.
Trying to figure out what. No, I'm gonna figure.
Okay,
He's getting me with how you had some.
now we need some more tools in our toolbox. And another very important tool is the ability to be the river. Okay, imagine this current, this flow, leaving the positive terminal of the battery and going around the circuit. And actually, it doesn't matter whether you go around clockwise or counterclockwise, it'll work either way. But every time that river meets a branching point, you have to ask yourself, is it going to split there 50-50 or some other way? Okay. And so if I'm ranking the bulbs in this simple circuit, I would say, well, all of the current has to go through A. It's an indicator bulb. Okay. But then when the river gets right here, it sees two paths and it can't tell them apart. They're identical. And so it splits 50-50. So B and C each get half of the total current through the battery. Okay. Now, they share equally because each branch has equal resistance. Now, what about these two circuits here? Well, it turns out that all the current from this battery goes through A, all the current from this battery goes through F, and then it splits 50-50. And so A and F would be the same brightness, that'd be the brightest, and then all the others are dim, but the same dimness. What I'm trying to get across with this is that the order doesn't matter. That simplifies things, okay? It doesn't matter whether they're closer to the positive terminal of the battery or closer to the negative terminal of the battery. because what goes around comes around. Okay? Now, B the river. Now, which is brighter, bulb C or bulb D? Tell your neighbor, which is brighter, bulb C or bulb D?
I was just thinking. Take them out, go at B and D, right? But you didn't split them.
Because he's in.
Okay, I hope you said bulb D is gonna be brighter. This goes in your toolbox. Current favors the path of least resistance. And I really, really, really beg you to use the word favors instead of chooses. The current doesn't all choose to go the easy path. Just more than half goes the easy path. Fred and all of his friends don't rush down the easy path. Just more than half of them go down the easy path. Okay, so A would get all of the current, D would get more than half of the current through the battery, and B and C would be equal to each other. Now, folks, if I had to justify this equal sign right here with a sentence, and that sentence could only have one word in it, what word would you want to use? I cannot wait to. I'm 70 years old. How would you justify that equal sign? Yes,
Because the voltage is constant across that.
what did he say? Oh, we're not gonna use the voltage word until Thursday. Yeah, wash your mouth out with soap. Series. Theory. If those bulbs are in series, Fred goes through one, he has to go through the other. Okay? If they're in series, they have not only the same size current, it's the same current. It's the same flow. Okay? So be the river here. Start with the positive terminal and go around, and every time you get to a branching point, ask yourself if you split 50-50 or some other way. Rank those bulbs. This would be the type of question you could expect on an exam. What's the brightest bulb, the second brightest bulb, so forth.
And then there's
Oh, that one drawing here. More of it's gonna go to some year.
Good thing we
We did it.
Okay. Let's do it together. The river leaves the battery. And when it gets to this first junction, does it split 50-50 or some other way? 50-50, because those two paths look identical to each other. So A and B each get half of the current through the battery. And then the current comes back together. This is the total current through the battery. What goes around comes around. And then it reaches this junction. Does it split 50-50 or some other way? Some other way. I get more than half going through E, less than half going through C and D. Okay? And so that means that E is going to be the brightest bulbs. A and B are going to be equal to each other because they each have half of the current through the battery. And then C is going to equal D. And that equal sign can be justified with the word series. Series. This equal sign can be justified by parallel paths that are equal resistance. Yes,
how can the then sign be justified?
I'm sorry.
How can greater sign for E be justified?
Oh, because E gets more than half and A gets exactly half. And more than half is If I told you you can have more than $500,000 or you can have $500,000, you know what you're gonna choose.
Why?
Why?
Why does E get more than half?
Because when it got to this point, it could either go to a easy path or a hard path, and current favors the path of least resistance. More than half will always go on the easy path. Less than half will always go on the hard path,
Okay.
okay? Not everyone chooses to be a doctor, okay? Fewer people go that path. It's harder, okay? Okay, now, in your homework, you had this problem here, 14.3. What happens to these two bulbs when I close that switch? Talk to your neighbor. What happens to bulb A and what happens to bulb B?
Half of their. Yeah, you're getting half of.
It's gotta be, no.
They're in both.
It's like infinitely.
All of the.
So there's no resistor on the. So.
Question. I don't think, I think that also means that, yeah. Yeah, because like the total. It's gonna get, it's going to, sorry, wait, hold on.
All that circuit.
Yeah. It's good, right? Confident after.
That is good. Particularly here.
Not.
Oh, it's a perfect.
I draw them out too. And when I was like, oh, this is like, well, I gotta actually.
Okay,
Yeah.
first of all, what's gonna happen to bulb A? Get brighter, dimmer, or stay the same? Shout it out. Brighter, yeah, why? Because I'm adding a path, and it's a really good path. And whenever I add a path, I lower the resistance of the circuit, the current through the battery goes up, and all the current through the battery goes through A. What about B? Brighter, dimmer, or the same? Yeah, not only dimmer, out, okay? I'm gonna close that switch by just taking a wire and putting it from one side of bulb B to the other side of bulb B. Watch what happens. Okay, bulb A got brighter and bulb B went out. And we say that bulb B is shorted out. And this is an exception to the rule that we just developed when we said current favors the path of least resistance, that the easy path gets more than half. When one of those paths is a perfect wire with zero resistance, all of the current, Fred and all of his friends go that way. And we're always going to assume perfect wires with zero resistance. And in practice, the resistance of wires tend to be so much smaller than the resistance of a bulb and other elements in your circuit that that's a pretty good approximation. Okay, so it's shorted out. All of the current has to go through A, but then when it gets here, all of it goes through the wire and none of it through bulb B. Okay. Now,
Hear me out.
in the tutorial, you found that sometimes our current model gives us answers which are just not answers. Okay, it falls apart. It falls apart. And that's because this model is a qualitative model that doesn't give us numbers. Let me show you what I mean there. In this simple circuit, with the switch closed, A is going to be the brightest and B and C are going to be equal. We've seen that before. Okay, B and C each get half of the current. If I open that switch, we have A equal B. They're in series now, and C is out. Is C shorted out? No or heck no? Heck no. It is out because it's on an incomplete path. Now, some of you are saying, Greg, out is out. Out is out. No, if it's on an incomplete path, your room's going to be dark. If it's shorted out, your house is going to burn down. Those are different. the insurance company treats those differently, okay? When I have an incomplete path, I lower the resistance through the battery. With a short, I increase the current through the battery. Now, what if I had taken, instead of this wire going from here, one side of B to the other side of B, what if I'd gone from here to here? What would I be shorting out? Yeah, everything, including the battery. And the wire that I put from here down to here would melt. Okay, so much current would flow through it that it would get really, really hot, and it would, if it's in your wall, it would start a fire. And that's why you've got the circuit breaker that's sitting there waiting for high currents, and it pops itself. Back when I was alive, we had little fuses that had a piece of material in there that would melt whenever you got a high current, and then you'd have to go and replace the fuse. But they were different times. We were happy. We didn't know. Okay. Now, the question is, what happens to B as we open that switch? Now, I know what happens to A. A gets dimmer. I've removed a path. I've increased the resistance of the circuit. I've lowered the current through the battery. All the current through the battery goes through A. A gets dimmer. But what about B? Okay. I know that with the switch closed, B gets half, 50% of the current through A. When I open that switch, two things happen. B's share increases from 50% to 100%. But the total current that we're sharing goes down. And our model doesn't tell us how much it goes down. It just says it goes down. If it goes down a little bit, B's going to get brighter. Okay, that's bigger than that. But if the current through A goes down a lot, B's going to get dimmer. And our model is not going to tell us which is going to happen until Thursday, when we develop a second model for voltage that we're not supposed to say today, right? Now, I call this a pizza problem. If you're hungry, would you rather have half of a large pizza or all of a small pizza? What question comes to mind? Yeah, how much smaller is the small pizza than the large pizza? Okay, it's like this.
What kind are they?
I don't.
Let's see. What's your name? Evelyn? Evelyn? And let's see. What's your name, sir? Brendan. Okay. Brendan's my son and Evelyn's my daughter. And I come to Evelyn and I say, you know, I got good news and bad news. Brendan, he messed up one too many times. Again and again, he keeps messing up and he is out of the will. You get nothing. Okay, you get it all. The bad news is the stock market tanked today. Now, is Evelyn better off or worse off today than she was yesterday? We know that Brendan's worse off. He's out of the will. But with Evelyn, we don't know. It depends on how much the stock market tanked today. She gets 100%, but 100% of what? Okay. See if your neighbor is following this pizza problem. On Thursday, I will teach you a second model for electric voltage. And with that second model, you can solve, I was going to say all circuits, but that's not true. Years ago in Montana, I put an exam question on the exam. And when I went to write the key, I found that it gave a pizza problem with the current model and a pizza problem with the voltage model. Unfortunately, I had already Xeroxed that exam 350 times, so I had to deep six that. And I took that exam question, I put it in my desk drawer to remind myself never to ask that question again. But all the other questions you can solve. Okay, so I've got this circuit. It's a fairly complicated one. I've got it on the board here. And the question that we want to answer first, which bulb is brighter, A or D? Tell your neighbor.
There's. Well, we're gonna go to here.
Okay, I think it's that gets to the back of the map.
He said the. I used to try to drink that. All garbage.
Start. It's an object. That's just straight.
I'm struggling.
Because then if he is gonna be set. Have the least resistance. Yeah.
Okay. Which one is gonna be brighter? Shout it out. Yes, okay. Again, what you want to do is figure out which of these branches has more resistance. And the way you do it is you draw them the same, exactly the same, and you ask what's missing. And what's missing is bulb C. And did I pick up my eraser? I did not. So I added that in parallel, making this an easier path and this a harder path. And so more of the current is gonna go through A than D. Okay. Now, what happens to A and D when I close that switch? When I close that switch?
These, so there's a split. It's just
gonna-
So D and. so,
Okay,
You have a straight up line.
He just.
there's the circuit, and you can see that, we were right. A is brighter than D. I want to, before we close the switch, I want to point something out. Does bulb B look half as bright as A? No. Is the current through bulb B half as much as the current through A? Exactly half. How do I know? Well, these two paths look the same. Everything that goes through A has to get back to the battery. Half of it's going to go through B and half of it's going to go through C. What I'm pointing out here is that half the current doesn't mean half as bright. It's not linear like that. Okay. All we can say is more flow, more glow. We can't say twice the flow, twice the glow. Okay. Now, if I close the switch, that's the same as shorting out bulb B. I'm going to do that by just going from one side of E to the other side of E. Okay, so what happened to A? Nothing, okay, not a Garnix. Nothing happened to B and nothing happened to C. D got brighter, okay. This is the one thing that you still need to put in your toolbox. Paths that are parallel, that are connected directly across the battery are independent. If they're directly across the battery from each other, parallel, they are independent. And if I look at these two branches, branch one being A, B, and C, and branch two being D and E, I can see that in both cases, I have a direct connection with nothing but wire to the positive terminal of the battery, a direct connection to the negative terminal of the battery with nothing but wire. Same for this one over here. They are totally independent. What that means is that I can hit B with a hammer. I can unscrew it. It changes this branch on the left, but not the branch on the right. Watch, the branch on the right couldn't care less. Now, here's a caveat. There's two flavors of parallel. There's the parallel across the battery, which these two branches are. That's the independent kind. And then there's all the regular parallel. Okay, B and C are parallel to each other. Can you see that? But they're not independent. If I unscrew B, C changes. If I hit C with a hammer, B's going to change. Okay, they're not independent. It's only when they have their own connections to both sides of the battery that they are independent. I call it vanilla independent and tutti frutti independent. The vanilla is just ordinary. Okay. Now, why did D get brighter? Well, I added a path that lowers the resistance, finish your sentence, of the circuit. That increases the current, finish your sentence, through the battery. The left branch is independent. It doesn't change. So all the extra current through the battery goes through the right branch. And D gets brighter. D gets brighter. Okay. If instead I add this indicator bulb here, first of all, is A still going to be the brighter bulb? Yes or no? Yeah, all the current through the battery has to go through that indicator bulb. But when it gets here, it still sees an easy path and a hard path with the switch open. Okay. And so A is still going to be brighter than D. They're both going to be dimmer because I just added some more resistance to the circuit. Now, do A and D change when I close the switch? And the answer is yes. They are no longer independent of each other. The two paths are no longer parallel across the battery. Because if I look at those two networks here, those two branches, when I try to find a connection to the negative terminal of the battery, I can do that. But when I try to go to the positive terminal of the battery, I got something in the way. And so they're not connected to both sides of the battery with nothing but wire. They are not parallel across the battery. Now your house is wired parallel across the battery, the power supply. Throughout your house, you have a high line and a ground line, and everything's connected from the high to the ground, and that's what makes them independent.
So I don't know if you've ever like plugged in like a blow dryer and turned it on and the light goes out. Does that mean that we're adding like a kind of like a, what do we call it, an indicator bulb kind of, because it does decrease the light?
So you plug in a hair dryer and something goes out?
When you plug in a hair dryer, when you turn it on, sometimes the light goes down a little bit.
Oh, what we have been talking about is for an ideal battery that always stays 12 volts. With real life batteries, alkaline batteries in particular, if you try to get too much current from them, they try, but the chemistry can't keep up. It's always the chemistry that fails. It's never the physics. It's the chemistry that fails.
I agree.
Okay, go somewhere else, people. I'm tired of it. I love you, but I'm tired.
Yeah, I'll be.
Like, pretty straightforward.